In this work, we present toy docking dataset, a collection of data for fast prototyping of new learning-based algorithms for protein-protein interaction. Since AlphaFold effectively solved protein structure prediction and we have sufficiently precise models of proteomes, it's time to make the new step, predicting protein-protein complexes. To make process of testing new ideas fast and convenient, we cast the protein-protein interaction problem in 2 dimensions. This makes training fast and allows interpretable visualization of learned features. So, what is a 2D protein? It's an image of a shape. Each pixel can have a value either 0, that corresponds to an empty space, or 1, meaning occupied by the shape. Now imagine we have 2 shapes corresponding to a receptor and a ligand. The probability of finding the ligand in a certain translation and rotation with respect to a receptor is defined by the Boltzmann distribution that depends on the interaction energy between the 2 shapes. We set the interaction energy between the 2 shapes to be a linear combination of the correlations between the shape boundaries and initial images. Incidentally, this choice corresponds to the first published protein-protein docking algorithm by Kachalsky-Kajer. Now, 2 shapes interact if they pass 2 conditions. First, the lowest conformation has the energy less than -80. And the gap between the 2 lowest bound states is more than 20. Here, figure A shows the interaction shapes, figure B shapes violates a gap condition, and in figure C, 2 shapes violate both. Finally, to get the post-prediction dataset, we generate 500 shapes, select all interacting ones, and among them select around 1,000 pairs of shapes with the corresponding lowest energy rotations and translations. The goal of a learning algorithm then is to predict a new translation and rotation for a novel pair of shapes not seen in the training dataset. We provide several baseline algorithms for this data. ResNet baseline attempts to learn direct mapping between the pair of images to the translation and rotation of the ligands using ResNet 18 model. The training curve shown in the figure shows that this model cannot learn such mapping. The brute force baseline is a differentiable formulation of exhaustive 2D docking algorithm. It successfully solves the dataset, however, it's impractical in the real case of protein-protein docking in 3D. Finally, we propose a new algorithm inspired by the energy-based generative image modeling. It also solves the problem, however, memory and compute requirements of this algorithm are much lower than those of brute force approach. Here we show the comparison of the 3 baselines, one negative, one positive, and one new algorithm as an example of how one can use this dataset. Additionally, we provide effect of interaction datasets and baselines, and you can see all this data at our poster. Thank you.